Getting ideas across. Humans communicate with words, with sketches, and with gestures. We communicate so naturally that we are able to ignore how we communicate and concentrate on what we mean. But what happens when our listener is a computer? Just how natural can our interactions be then? Today, a group led by Hamid Alozi at the IBM T.J. Watson Research Center is investigating that problem by exploring a new kind of human-computer interaction. The paper-like interface is an experimental user interface that merges the display screen and the input device into a single unit. To enter data or commands, a digitizing pen is used to write directly on a combination digitizing tablet and liquid crystal display. As the characters or command gestures are written, they are interpreted by the underlying application. Misinterpreted characters can be corrected in place.
Writing with pencil and paper is so natural that we tend to take it for granted. With our system, we have the naturalness of pencil and paper combined with the power of the computer.
We have implemented this interface on a number of applications, each of which includes an appropriate set of command gestures. Any new application can be easily supplied with new gestures. Suppose we wanted to use an open-sided box as a command. If we wrote this symbol now, it would not be recognized by the system. After defining the field orientation and reflection of the box, however, we can redraw it. We see now that the system has learned the gesture.
The advantage of being able to define your own gesture is that you can select and choose the ones that best fit your applications. People who are using editors can define step marks that are used in editing type applications. Mathematicians can define their own mathematical symbols. The system is open-ended from that point of view.
An electronic notepad is clearly not the right interface in all situations. For large amounts of data entry, a keyboard is much more efficient. But if the main interaction is with menus or with data scattered across the screen, then we can save time by not having to position a cursor or type long command sequences. An application which ideally suits this criterion is the Lotus 123 Spreadsheet program. Our interface to Lotus 123 uses lines and brackets to mark ranges. Simple one-stroke gestures for summation, deletion, and insertion of columns and rows, and gestures for copying a cell into a range and copying a range into a target location. To compare our system with a keyboard interface, let's first look at three typical spreadsheet operations. Using a keyboard, we would copy a column of numbers by typing the copy command, marking the column to be copied, and marking the target position of the column. With our system, we use a single gesture to identify the range and a second gesture to specify the operation and target location. Insertion on a keyboard system requires the user to move the cursor to the desired location, then type the insertion command. Our interface allows the operation and insert location to be specified with a single gesture. Operations in a keyboard system are slowed down by the time it takes to recall and type complex notation and the time it takes to move the cursor around the screen. Directly accessing the screen speeds up the entire process.
It's important to remember that the system we've shown you is not a terminal emulator. It's not a spreadsheet program. The system is the interface to these applications, which allows you to interact with them using handwriting and gesture. As a research group involved with computer science applications, we're interested in this style of interface for several reasons.
Gestures have the power of macros. That is, a single symbol can stand for a complex sequence of commands. Most importantly, gestures are natural. Instead of having to remember a combination of keys or an abbreviated command name, we can write the same gesture on the screen that we would write on paper. And with the trainable gesture recognizer, users can define their own symbols. As we've demonstrated, our system presents a natural way of interacting with computing systems. It presents users with a novel paradigm for interacting, namely a pencil and paper-like interface. which is ideally suited to systems that require large amounts of two-dimensional access to information on the screen.
It's superior to a keyboard, that's superior to a mouse. Now, if one were to incorporate the system that we've developed on a hardware base that consists of the tablet, the display, packaged in a device the size, weight, and shape of a thick notepad, one would really have a truly portable computer.